everything.
We are probably, just a heads up, this is the last section in chapter 3.
Test.
Wait, that wasn't a test session.
It was a quiz.
That
We
was
have
a,
a test.
Test with
Test.
notes.
So this will probably take me a couple days, and then a couple days to review for the test. So test Wednesday-ish.
ish.
Okay.
Tuesday, Wednesday. Let's see. Today is just
So we could squeeze it in on Friday potentially.
Tomorrow.
tomorrow.
No, like next
It will be
Friday.
before next Friday. I'm going for Wednesday.
Not if the weather lady. as
Yes.
everybody
There is
said.
no snow in the forecast.
I think
Well, there
we
wasn't
get,
snow in the forecast last night. No.
I think we get like 6 inches of snow.
6 inches of snow on Tuesday night.
Yeah,
And we come back next 2 weeks from now. Miss Starkle says,
Hey, here's our test. I've been waiting.
Yeah.
I'll go this time though.
I plan on studying too.
I don't.
Alright, so linear approximation, it kind of seems like a weird place to slide this in because we talked about similar things way back a long time ago, but anyway, this is the sequence. So a linear approximation, we know that we have points on curves and it's sometimes hard to find out an equation for a curve, right? But it's really easy to write an equation of a line. And so if I were trying to estimate a point on this curve, what I could do is use a tangent line to get there. Okay, now, if this were my tangent line, is this point over here, are those a good approximation? No. But if I were trying to estimate this point on my blue curve, is that tangent line pretty good?
Yeah, that's
Yeah, and if I were trying to get it right here or right here, the tangent line is an excellent approximation. So the better approximation happens when your points are really close. So if I'm going to make my tangent line when x is 2, then it would be a good approximation for x values close to 2. And so we did this a kind of back at the beginning when we were like estimating slopes of tangent lines. It's related to that.
Is the tangent line the pink one?
So we know how to write the equation of a line, y equals mx plus b. If you're looking in your book, it gives this formula, and it tells you L is your linearization. To me, that just looks confusing, so let's think of it more. Instead of y, we will use the L notation for linearization, but just L of x or y equals mx plus b. M, the slope, is going to be from the derivative. So we're just going to write our typical equation of a line, but instead of y, we will use L of x. Let's try an example. So find the linearization of the function f of x is equal to the square root of x plus 3 at a equals 1, and use it to approximate the square root of 3.98 and the square root of 4.05. Can we all agree that we don't know the square root of 3.98? Yeah. Okay, Carson, what is it? Let's see if you're right.
I was speaking for the trees.
Oh.
1.98.
So, those are square roots that we don't know. But we could use a tangent line. It's a lot easier to plug an x value into y equals mx plus b than it is to plug it into a square root. Okay? So,
I was 0.01.
for this, we need a function. So that's my f of x. I'm going to write it, the square root, as a 1/2 power. Okay, and I am approximating this at a equals 1. So this is going to give me an order pair. When my a is 1, come in. Somebody just knocked on my door.
Definitely.
I thought so.
Come in. Hi, how are you?
So you missed CTA cookie last week because you had migraine.
You're so sweet.
You too.
I got you.
Yeah, I know you don't want that.
So if we plug in a 1, we get the square root of 4, which is 2. So 1, 2 is the actual point on this function. This is just a We're going to get an approximation for the others. Okay. To write the equation of a line, we need a point and a slope. We have a point. What are we going to do to get the slope? We're going to go. So, exponent comes down. Inside stays the same. Subtract 1 from the power.
And do the inside.
Derivative of the inside is 1. So I'm going to write this as 1 over 2 square root of x plus 3. Just because I'm going to plug a number in.
Oh, you flipped it the.
Yeah, I just wrote it back in radical form because I'm going to plug a number into this in a second. So to get my slope, that is f prime of 1. So if I plug a 1 in,
Get 1/2. No. 1/4. I don't know why I didn't.
so our slope is 1/4.
That 2 didn't get carried down.
So now I have a point and I have a slope. So we can write the equation of a line. Do you guys use just plug into y equals mx plus b, right? You're not in my class that likes point slope formula.
We are not.
They all blend together. at
What
some-
what class is that?
Class of freaks.
Free calc now. Mrs. Keller switched how she was kind of teaching that, so she really emphasized,
Oh.
and so certain
So
years
now
she
you have a bunch of
emphasizes
weirdos.
different things. So then I'm trying to like do it however
See
it's
what
taught.
works.
Yeah.
I don't even.
So is this? Did that become? That's
Point slope is
y
x
so
plus
Y
by.
minus y1 equals m times x minus x1.
Oh.
no.
No, I
No.
don't even know what that is.
Okay, let's just
Oh,
plug
is
into
this,
y equals mx plus
is
c.
this slope formula becoming 1, 1/4? What?
No, this is
No, that's just by itself.
Mhm. So y equals m times x plus b. So 2 is like 8/4 minus 1/4 is 7. So final answer, instead of y, I'm going to put L of x equals m 1/4 x plus b, 7/4. That is my linearization. Okay, that is a line. It's the tangent line when my x value is 1. So would it be easier to plug numbers into a square root or to a line? Definitely a line. So this would be used to approximate. This kind of strategy was used like back before calculators were quite so prevalent because you don't really need it if you have a calculator, but for more complex things, this would work. So now I want to use it to approximate the square root of 3.98. We need to be a little bit careful here. Under the square root, it's x plus 3. So if I'm putting in 3.98, what is my x value? 0.98. So
Oh.
the square root of 3.98, because the equation was the square root of x plus 3, that means my x is 0.98. So we're going to plug a 0.98 into our linearization formula, and let's go ahead and just use our calculators. And so that gives me
1.995.
if the other one was 4.05. So if I'm doing square root of 4.05, what is my x value? And again, that's only because this problem had x plus 3 under the radical.
Are we out of the part where we have to show a bunch of work? Like, can we
Yeah.
go back to nonsense land?
Yes, right now you do not have to show a lot of work. Alright, so we've got our two linearizations. I also asked if these were over or under approximations. So a couple ways you could think about it. Obviously, could do the square root of 3.98 and see if this is higher or lower. We could also think about a graph. Square root, looks like this. The +3 moved to the left. So if you are drawing a tangent line, is it going to be above or below this curve? Above. So that means these approximations are overestimates because they came from a line above.
I'll agree with this one.
That is very
That's not-
sloppy.
Is that how you spell that word? Yes,
Yeah, it's just super sloppy. I don't know what happened. My
Just one word? Shoot, dog.
Okay. The next slide, I just put a table of these values to kind of illustrate. So if you were doing the square root of 3.9, our linear approximation is 1.975, and that's the actual 3.98. You can see we were really, really close. We said 1.995, and it's actually 1.99499. So we were super close. 2 is obviously works out perfectly, and it goes the other direction. So we can see here, like at 6, it is further off. The further you get away from when x is 1, then the less accurate your approximations will be. Is that okay with everyone? And I think, what I just put, so as the x gets further from 1, the estimate
it's less accurate.
gets less accurate or gets further from the true value. Let's try and do that one. So I want to find the linear approximation to the function f of x equals the square root of 1 plus x near the point a equals 0. So we're trying to write the equation of the line. Line y equals mx plus b. So we need a point and a slope. What is my point going to be? 0, 1. And I got that by plugging 0 into my function. So my function is 1 plus x to the 1/2. So what do I have to do? Derivative. 1/2. 1 plus x and a 1/2 times derivative of the inside is 1. So I could write this as 1 over 2 square root of 1 plus x.
Are A and X the same thing?
Yeah, instead of, it just seems confusing to write x equals and you have to add it, unless you plug it into later, so they typically say a instead, but
But
it's
they're
the
the
x value. So your slope, if we plug what value in? Mhm. So equation of a line, y equals mx plus b, so our y-intercept is 1. So our linear approximation is 1/2 x plus 1. I didn't ask you to calculate any other values there, just to find the limit. Is that okay? Do you guys think you're ready to try one on your own yet?
Not 3A.
Not that one?
Not
What?
3A.
What's wrong with that one?
Oh, I can do.
I-
three.
Don't let Carson speak for me.
Okay,
Well,
so if we're going to write the equation of a line, we need a point and a slope. So my point, the x value of this ordered pair is 0. If I plug in 0 to my equation, we get 1. Alright, 1 over 1 minus x for derivative. I could write that as 1 minus x to the negative 1 power.
Now I can do it.
Now you can,
I just couldn't think of how I wanted to do that.
I mean, you could do quotient rule.
No.
So exponent comes down, inside stays the same, subtract 1 from the power, times derivative of the inside is negative 1. So that gives me 1 over 1 minus x squared. Alright, so we need our slope. So we plug what in? 0, because that's my a value. And we get x plus b. My intercept is 1. So the linearization is f of x equals x plus 1. Why don't you guys try b? Alright, so our point, it
What did you get, Grant?
told us at the beginning that a was 0. If you plug 0 in here, we get out 1. Our derivative would be 3 halves, 1 minus 2x, subtract 1 from the power, so 1 half. Derivative of the inside is negative 2. Mm-hmm. You what? Oh.
I forgot how to find the one.
So our slope, if we put a 0 in, we get negative 3 times the square root of 1, which is negative 3. So y equals mx plus 3, y intercept is 1. So linear approximation is negative 3x plus 1.
You did that in a lot less steps than I did.
You are so proud. That is rude.
Oh no,
It's pretty sad.
Grant this morning, he was grading my paper in chemistry and laughing at every
What?
question I got.
No.
Really?
I'm gonna stand up for Grant.
You know
here.
what?
She was
So
doing
if
the
it
same
makes
thing.
Let's look at this one. So if I want the linear approximation formula to approximate 122 to the 2/3 power. So it's a little bit different. I didn't give you a function and an a value. I told you this is what I want you to find the estimate of.
We just make it.
So we have to make a function and an a. That would help.
Perfect.
So keep in mind, a 2/3 power means we have the cube root of this squared. Okay, so if I'm going to have a function, my x is taking the place of this thing. So for derivative purposes, it's better to write it as the 2/3, but I need to see this for a second so I can take my a value. If I'm going to do this, a has to be something close to 122 that I could find the cube root of.
I could not think of any single perfect square or anything.
Yeah, so start, like, if that's the problem, start with your cubes. So 2 cubed is 8, 3 cubed 27, 4 cubed 64, 5 cubed 125, 6 cubed 216, and you can go from there. Okay, so,
The way you rattle those out like a sleeper engine.
so my point, if this is 125, if I plug that into my function, the cube root of 125 is 5, squared is 25. So that's the point. And now I need a slope. So my derivative, 2/3 x, 2/3 minus 1.
Negative a third.
you need to, you can realize this is like saying 2 over 3 times the cube root of x, if that makes it easier to plug in a number. So if I put in 125, cube root of 125 is 5, so we get 2 over 15 for our slope. So now I have a point, I have a slope, so y equals mx plus b. We get 25 over 3 to the y-intercept. So the linearization is 2 over 15x plus 25 thirds. So that is the line I could use to approximate. And it will work for x values close to 125. So which one did I actually ask you to approximate?
122.
No, just really just plug in 3. No, never mind.
Yeah, the other one we didn't put in the actual.
Because it added.
And we could have made a more complex equation that did that. We just didn't. So I get a linear approximation of 24.6. How close are we? What is 122 to the 2/3 power?
124.
24.598, and our approximation is 24.6. So we were pretty close.
That is pretty darn close right there.
Alright, you guys, let's do one last problem for today. So, what would my function be?
5.
Like my,
Next
I
to
know,
the
but isn't that
1/3.
just
it's a cube, no, that's the square root. This is a cube. So, the cube root of x, or x to the 1/3 is my function. What is my a? Something close to 25 that we can do the cube root of. Not
Oh.
3, 27.
3.
Okay.
Yes.
So, 27/3 is the order pair, because the cube root of 27 is 3. We need a slope, so derivative. And you don't have to take the step where you write it in radicals, but if I'm going to be evaluating things without a calculator, that helps me. So we need, our slope is when we plug in a 27.
I didn't write it on you did.
What's the cube root of 27?
3, 9, 27 again.
So our linearization is 1 over 27 x plus 2. Alright, now I want to estimate 25. So if I put a 25 into this,
Why do you estimate 25 and not cube?
we're trying to estimate the cube root of 25, so I'm using this whole equation to do it.
Backwards.
Mhm. So if I plug 25 into my equation, I get 2.9259. And if we check the cube root of 25,
2.93.
2.924. so we were pretty close. Alright. Any questions so far? This is our stopping point for today. Tomorrow we are going to talk about differentials and error, so this is what you are ready to start, and then tomorrow we will finish.